I'm going to attempt to explain quantum physics to you. Every single person watching this can learn quantum physics, and I'm going to explain it from the most basic details to the most extraordinary ideas like superposition, quantum entanglement, and many other things like why is the sky blue? So many different quantum phenomena that happen all around us, and I'm going to explain them now. So quantum mechanics is a very deep and rich subject, which you can't really get any good explanations from a 10 to 15 minute YouTube video, which is why I want to make a whole video series dedicated to exploring quantum mechanics and to enrich you with the knowledge necessary to fully grasp some ideas of quantum mechanics without relying too much on very specific examples or very specific ideas. Now, that doesn't mean I'm not going to go over the most interesting parts of quantum mechanics like superposition and entanglement. Those are some of my favorite parts. I'm definitely going to go over them. It just means that I'm also going to have to go over some of the more boring details like the foundations of quantum mechanics and where it all comes from, explanations on how to explore quantum mechanics, things like that. So soon we'll get into more interesting and fun stuff. But right now, we need to go back in time, go back to how quantum mechanics was discovered and show how it comes to be, really. So the real backbone of quantum mechanics is the Schrodinger equation. Now, the Schrodinger equation is a differential equation that you can solve for solutions of functions for quantum mechanics, quantum systems. So now, let's look at the Schrodinger equation itself. Now, like I said, the Schrodinger equation is the backbone of quantum mechanics, and there are two of them, in fact, because it's that important. So now the first one we're going to look at is the time-dependent Schrodinger equation. Now, like the name says, this Schrodinger equation depends on time specifically. So if you have like a potential that changes with time, this is what you're going to use. Most of the time, we're not going to be dealing with that. So what we are going to be doing is splitting up the time and the position part of the Schrodinger equation. So we get the time-independent Schrodinger equation. Now the logic behind this is that whatever happens in time, your system will evolve in time independently of what happens to it and its position. It's a little strange to think about, but it makes sense in quantum mechanics. Now, what we're going to do is use this time-independent Schrodinger equation, and I'll show you that it's really just written as a term of conservation of energy. So what you can obviously see on the left side of this equation is E. That's going to be the total energy of the equation, and that's analogous to this side of the Schrodinger equation, the time-dependent version. And all this is saying right here is that when the equation time evolves, then it's not going to change its energy. It has consistent energy throughout time. Now, let's look at the other side of the Schrodinger equation. Let's first look at this part right here. It looks pretty strange. First thing to know, h bar is just a quantum mechanics constant. It's in all of quantum mechanics. When you see an h bar in an equation, you know you're doing quantum mechanics. So h bar is just a constant. And that constant has a specific value. I don't remember the specific value, but know that the units of it are joule seconds. That'll actually come in handy later when we talk about spin. Now, let's look at this little strange thing right here, this upside down triangle. All that means is to take a derivative with respect to position. And so that's pretty interesting. Why don't we just write the derivative? Well, this is actually also in 3 dimensions. So you want to take the derivative in respect to all 3 dimensions. So that's just a faster way of writing that. Well, let's talk about a 1D system right now. So let's ignore the the y and z variables, and we're only going to focus on x. So now that we know that's a derivative, what's this 2m here? Well, if you remember from classical mechanics, kinetic energy is equal to 1/2 mv squared. Now, if you also remember from quantum mechanics, momentum is equal to mv. Solve for v. V equals p over m. Square it. I'm running out of room. So we get kinetic energy is equal to 1/2 m p squared over m. M's cancel. Or, well, just one of the m's cancel because that's squared. And so now I'm going to write kinetic energy as a T, a capital T now, because that's what we do in quantum mechanics. We change the numbers, we change the letters that we use. 1/2 p squared over m. That is kinetic energy. And that's actually completely classical. That's in classical mechanics as well. But we like to use momentum in quantum mechanics to write it in terms of energy. So as you can see, this is actually just this, but with a factor of h bar on it as well. So that's actually pretty cool. You can write this in terms of the momentum. Now, let's also say this potential. If you remember what a potential is, potential energy comes to mind. Let's take example a spring. So the potential energy of a spring is 1/2 kx squared. Now this is why we have potential in here, because potential is a function of position, or x. X is our position. So we can write v of x in terms of this. That could just be our potential, simple as that. And so now we understand each component of the Schrodinger equation, but what do we do with it? Well, when we have a potential, we can actually solve the differential equation. I'm not going to do that right now, but let's say I give you psi of x equals sine of x. Well, that means that the wave function looks something like this, like a sine function, with this axis being psi, this axis being x. Now that's cool, but what does that mean? Well, if you remember from before, quantum mechanics is actually a statistical theory. So this wave function is actually a probability distribution. Now what does that mean? That means if we were to measure the position x of this wave function, we would most likely find it where the probability distribution is a maximum or minimum. Maximum or minimum now, because there's some inherent complex variables in quantum mechanics. And so to combat those complex variables, to find real solutions, we actually have to square the wave function. So an actual probability density would look like this. That would be what the probability density would look like. You're most likely to find it here and here. So that's pretty interesting. We have wave functions in quantum mechanics. It's a statistical theory of quantum mechanics, meaning there's no absolute position. There's only probabilities of measuring at a certain position, as well as the Schrodinger equation itself being written as basically a conservation of energy formula. All right, and that's it for the Schrodinger equation today. The most interesting parts in quantum mechanics are also the ones that are hardest to understand really conceptually. You can watch videos and read articles and take all the information at face value, but in reality, you're not truly getting it. You're not truly learning anything. You're just kind of reading something and taking it at face value, not fully developing an understanding of quantum physics or quantum mechanics at all. And so my goal really is to make it easier to develop that understanding of quantum mechanics, quantum physics, and quantum phenomena. So next time that you read something or watch a video, you can really truly understand what's going on and what's happening. So you're not reliant on other people's information. So I hope this helps. And I hope we can all learn more about physics, learn more in general at all, and have fun while doing it. Awesome. Thanks for watching. Hit subscribe if you like this and you want to see the next video, because the next videos are going to be super popular, hopefully. The Heisenberg uncertainty principle, some more quantum solutions, and quantum superposition maybe. We'll get into them eventually. All right. Thanks for watching. Bye.